Welcome to the construction of the Civic Center. We are Greenwood, and we are delighted to expose the design of our building. Our priority is always the functionality of the finished design and the satisfaction of the client. These are, however, not all of the parameters and limitations met by our team when undertaking such a task. The Civic Center to be constructed is a 5-story building comprising a library in the lower ground floor and council offices in the upper floors. The building is to be constructed on the side of a hill, so the offices on the first floor can be accessed on one side and the library on the lower floor can be accessed on the other side. The project will involve an excavation into the side of a hill, the construction of the building and its maintenance for the next 30 years. The topics that will be discussed in these presentations are chosen design, building structure, materials, sustainability, safe construction, emergency procedures, and conclusions.
This structural system allows the design of the floor plans to be carried out independently from the frame, which provides a more efficient use of the available space. Additionally, this layout and the simplicity of the structure will speed the calculations, which will reduce the cost of the production. The grid system consists of a rectangle in which the external grids are 9 by 9 meters and the middle grids get smaller as shown in the figure. As you can see, the grid has one line of symmetry along each axis. This means that the calculations are greatly simplified as any 1/4 of the floor plan layout is calculated, and it can be mirrored across the neighboring section. This will not, however, apply to the library ground floor, as it is the exception of the rule of this symmetry. The load path will be orthogonal through the frame structure down to the foundation, the exception to the north face of the building that it will transfer down orthogonally until it reaches the retaining wall, which will be also carry the vertical loads working as a bearing wall, together with the horizontal loads exerted by the soil due to the chaining level across the site. The retaining wall will be connected to the foundation level. This design will be supported by the shear wall of the stability core, which will also hold the placing for the fire exit circulation.
The structure of the building is made up of various components. These components are going to be predominantly made out of reinforced concrete and be constructed on site. Since the building will be situated within a hill, excavations and the necessary groundworks will be done to allow the construction of the retaining wall. The retaining wall has been designed to withstand the horizontal pressure exerted by the retained material from the hill, preventing it from slipping and collapsing back into its natural form. The retaining wall will also carry vertical loads from the various structural components. The wall will be composed of a 6-meter high wall with a thickness of 600 millimeters and a strip footing of 5.5 meters wide with a depth of 600 millimeters, giving it a total height of 6.6 meters. Foundations will consist of isolated pad footings being placed at the bottom end of every column. These shallow foundations are suitable to use as the imposed loads by the structure are relatively low in comparison to the bearing capacity of the soil surface. A total of 23 pad footings with a depth of 600 millimeters will be constructed and will vary in sizes. Columns along the perimeter will be supported by footings of 3.3 by 3.3 meters and 2.3 by 2.3 meters. Columns within the center of the building will be supported by 3.7 by 3.7 meters footing. Columns of 500 by 500 millimeters will be placed around the perimeter of the building and throughout the center. They will start from the lower ground floor and continue up to the roof terrace. Columns will have a reasonable distance between them as to reduce bending moments in beams. Columns along the perimeter will sustain loads from the outer perimeter beams, and columns that are within the center will support loads transferred from the floor slabs. RC beams will only be placed along the perimeter of the library and office levels. The lower ground floor and fourth floor will have beams with a depth of 400 millimeters and width of 300 millimeters. The first, second and third floors will have beams with a depth of 360 millimeters and a width of 300 millimeters. The beams will help support walls as well as floor slabs which will be connected to them. For the lower ground library, a floating slab with a total of 550 mm thickness will be constructed, composed of different materials. Upper floors will have a waffle slab system put in place, as large spans can be constructed, making it suitable for the large open spaces to be created. The first floor and roof terrace will have a 400 mm thick slabs, and the second, third and fourth will have 360 mm thick slabs. Waffle slabs will range in sizes, the largest one being 9 by 9 meters and smallest being 6 by 6 meters. These types of slabs is much stronger than conventional flat slabs, whilst having less self-weight, making it more economical and sustainable choice.
.6 ton of carbon dioxide is generated in the production of 1 ton of cement. This number represents between the 6% to 8% of the total pollution generated globally. A more environmentally friendly cement replacement can be GGBS, that can replace a substantial portion of the Portland cement component, generally about 50%, but sometimes up to 70%. It comes from the steel industry, as it is a granulated blast furnace slag, which is extracted from iron by grinding granulated iron into smaller particles. Approximately a third of all UK ready-mix concrete deliveries contain GGBS. Benefits that GGBS offers: considerable sustainability benefits, lower early edge temperature rise, reducing the risk of thermal cracking in large pores, minimizes the risk of damaging internal reactions such as alkali-silica reaction and delayed ettringite formation. High resistance to chloride ingress, thus reducing the risk of steel reinforcement corrosion. High resistance to attack by sulfites and other chemicals. Better workability, making placing and compaction easier. The percentages of GGBS used in each structural element of the building varies depending on its function and exposure class. The external elements exposed to permanent contact with soil or rainwater and freezing are mainly retaining walls, edge beams and foundation, which have a higher exposure class, meaning that only a 40% of cement replacement can be used, so the material's performance won't be affected. On the other hand, the internal elements like waffle slabs or columns have up to 60% of GGBS, as the exposure class is lower.
With the growing concerns about the environmental impact of new structures, it has become an ever-growing factor within the role of an engineer to guarantee the sustainability of a project and the reduction of the functional carbon footprint. Based on BREEAM, this building ensures an accordance to both the mandatory and aspirational goals of any structure concerning environmental impact. An inspection of the site shall be made before arranging a handover meeting to ensure building services and fabric defects are identified and rectified. Seasonal testing of the building system will also be conducted to review the thermal comfort, ventilation, and lighting to make sure they remain operating as required.
The use of LED lights in the building will contribute to the sustainability by reducing power plant demand and lowering greenhouse gas emissions, as it consumes less energy and is up to 80% more efficient than conventional lighting. Daylight sensors, motion detection sensors, and switches can also be added to the outdoor spaces to monitor pedestrian traffic and switch the lighting on and off based on brightness levels. The mixed use of these sensors will ensure greater efficiency combined with cost savings. To maintain indoor air quality, smart airflow will be installed indoors to draw air up the building's 6-story ramp and out through the vents in the roof. Sensors can be installed too to reduce energy consumption. Low carbon concrete, aluminium ceiling, rain and water harvesting, or water panel and ventilation systems. These will reduce energy consumption required by the heating and cooling system of the building. A combined heat and power unit which generates electricity while also capturing usable heat is produced as a byproduct in this process, will also be implemented. Wasted heat energy from this process is recycled for heating and cooling. It is expected to save 500 to 750 metric tons of CO2 each year. Furthermore, solar panels, green walls, green roof, and timber cladding will also minimize the production of CO2. An efficient method to save up potable water in the building is a rainwater harvesting system. This installation makes it possible to save up to 50% of potable water, and by doing so saves money. The water collected will be used for sanitary use and it can be purified for human consumption if required. This system does not require chemicals for water treatment, which makes this method environmentally friendly. It is well known that the vegetation converts CO2 into oxygen, therefore the air quality will be improved alongside the health of the people that will work there. Green roofs will contribute to the building's sustainability by supplying insulation in the winter and reducing air conditioning in the summer, lowering energy usage. Green roofing extends the life of your roof by shielding it from damaging effects of the sun, wind and rain. A living wall certainly improves the appearance of the building and people's well-being by increasing biodiversity. The green wall of the building functions as a rain screen, so benefits like this cover the cost of maintenance of it.
This project includes the necessary precautions and procedures involved to protect all staff on site, as well as minimizing the disruption to nearby residents and natural environment surrounding the site. It will be constantly reviewed and revised throughout the span of the project to add any necessary changes or improvements. An extensive health and safety system is the most vital part of this report, in which we must set the highest standards as hundreds of lives are at risk during this project. Completing this construction with no injuries or accidents is one of our main targets.
Fire routes are designed for both horizontal and simultaneous vertical escape. The multi-story building is provided with alternative fire escapes as the top floor height exceeds 11 meters and the travel distance exceeds 18 meters. Additionally, as the multi-story building requires multiple vertical escapes, a person from each part of the building should have access to more than one stair. Those 3 stair cores are provided at the corners to comply with all the requirements. Escape route design is subjected on the calculation of occupants across the area of each floor. The floor space factor allocated for office building is 6 meters squared per person. Based on the area of 4 office floor and the library, the total sum of occupants across the entire building is 786 people. Access to stairway is provided with a door of 1.5 meter width, which is subjected to the stair width provided and guarantees access to wheelchairs. A minimum area of 900 by 1400 mm are provided for refugee on each stairway and will not be of obstruction for escape flow. Based on the above parameters, the staircase has been designed to comply with the minimum requirements set in the Building Regulation 2010, Approved Document B, as well as Approved Document K.
The project produced in this report not only fulfills the client's specification, but does so while providing an economic, efficient and elegant design. The project provided an opportunity for near limitless innovation when considering both the construction procedures and the materials. The building will have a modern contemporary feel with its stylish minimalism, the bare concrete ceilings made possible while maintaining a sleek design due to the shape of our implemented waffle slabs. These give the ceiling a far more captivating form. The bare concrete itself serving another purpose entirely and allowing maintenance checks to be carried out rapidly and with ease, as any sign of creep or failure in the concrete will become visible to the naked eye. It's these kind of adaptations implemented by our skilled design team that collectively reduce the cost of the structure, making it the most financially attractive option for the client. The freedom given to the group in the brief allowed for cost reductions and enabling an environmentally conscious product which adhered to all relevant local and continental legislations. The simple structure scheme maximizes the flexibility of the project while reducing the production time, so it can be considered the most time-saving layout while simultaneously providing a solution for all the requests. This project was a great example of the sheer fact that a design does not always require complexity in order to achieve all of its design purposes.